This is group 5 for class ME 4271. We're going to be talking about a condenser shell and tube heat exchanger using refrigerant R22 and water. What we'll be going through is our problem statement, the results from our calculator, the results from our CFD, cost analysis, and final remarks overall. We were tasked to design a condenser shell and tube heat exchanger with a rated tons of 2 tons using refrigerant R22 condensing vapors to liquid, using water as a coolant with an inlet temperature of 80 degrees Fahrenheit and in a horizontal configuration. To start off, the team first needed to find the appropriate Nusselt number. During condensation, we utilized a different Nusselt number because of the condensation film. We found that the equation found could be used for both shell side and tube side configurations of the refrigerant. On this slide, we can see the operating parameters. On the right in red boxes, we can see that for the tube side, the energy transfer is up to our problem statement. For the shell side, very identical slide. And we can see on the right that the final iteration of a new shell and tube is much higher, and after 1 year still meets the requirement.
So we modeled our shell and tube for only the single pass shell and tube condenser where it condensates on the shell side because it met the requirements and required less tubing for the tube side condensation. R22 comes from the top of the shell while water comes from the bottom of the shell. R22 comes in at 35 degrees C at saturation temperature and saturation pressure. The mass flow rate is 2.2 kilograms per second. For the water, it comes in at 27 degrees C with a mass flow rate of 1.5 kilograms per second. And then you can see our model at the bottom with the dimensions that we used for our shell and tube. Here are the CFD results. This shows the temperatures inside the tube and the shell. You can see that the shell actually cools down as it passes through the shell side and goes through the baffles with the mixing. Here's an animation of the shell side flow and tube side flow. The shell is moving up and down through the baffles there, and the water is flowing from right to left. These are the results from our CFD. It calculated the outlet temperatures, which are different from what we got for our math model, but it does cool down and heat up as expected. Also, there is a phase transition because of the warning given in the solver. SolidWorks doesn't directly tell us if a phase change occurs, but this warning when it does a flow simulation tells us that there is a phase transition.
So we performed a cost analysis for when our R22 flows through the shell side of our heat exchanger. This cost analysis was done by taking different sizes and different prices of stainless steel tubes from McMaster-Carr, finding the dollars per meter cubed, and then multiplying it by the volume of our heat and tube exchange, shell and tube exchanger that was found from our SolidWorks model. Our total cost came out to $14,295 approximately. We also took into consideration that R22 has a very high cost. This would lead to a high evacuation cost. This high cost is due because there's a low supply, since it has found to be harmful for the environment and now being phased out. Next slide. This slide shows our analysis between our two different heat exchangers, when our R22 runs through our shell side and when it runs through our tube side. The green shows which one performed better. Since our shell side had better performance in 3 categories, that's what we decided to do our PDR, our CFD, and our cost analysis for. Next slide. So our final remarks was that compared to other heat exchangers, our heat exchanger was fairly long for the power rating. Our CFD exposed hotspots, and our CFD and math modeling varied in its performance. We also know that refrigerant has a high cost. Right?